Would like you can. All right. All right, so we're going to talk about triple integrals today. So for this, for what we're talking about today, we are saying we're starting with a function f of x, y, z. So with our double integrals, we always said z equals f of x, y. Today we're saying we have some function of x, y, z. And our function is a nice function, so we're going to say it's continuous over a bounded solid region. So we have a solid region. And we're going to call our solid region Q. So we're going to draw, like we've done before, draw a sketch of our arbitrary solid region. So here's our solid region above the first octant. And what we're going to do for triple integrals is, rather than dividing this region into little prisms, we're going to divide it into little rectangular prisms with our base on the xy plane. We're just going to divide this region into small rectangular prisms in little block shapes. So there's a little piece of little volume element in our solid region. So the solid region is f of x, y, z. We're going to say that the coordinates of this little piece of volume, this little chunk of the solid, is at x sub I, y sub I, z sub I, and the dimensions are going to be, this side would be delta y sub I, this side would be delta x sub I, and our height would be delta z sub I. And we're going to call this little piece, the volume of that little piece, delta v sub I. So delta v sub I, we're saying that we're dividing it into little rectangular prisms. So it's going to be delta x sub I, delta y sub I, delta z sub I. And x sub I, y sub I, z sub I is a point in that little box. To find the volume of the entire solid, we're going to form the sum. And this should be familiar by now. Is this sum for I equals 1 to n, however many pieces we divide this into, of so what I want to do is if we just form the sum of delta x sub I, delta y sub I, delta z sub I, we would get the volume. The volume of the solid would be the sum delta x sub I, delta y sub I, delta z sub I. And if we take the limit as delta v sub I approaches 0, and again, being a little loose with that definition, what we're saying is the longest diagonal in these little solids the length of the longest diagonal approaches 0. So in essence, we're saying delta v sub I goes to 0. So the volume of the solid, this would correspond to our definition of a double integral if we were talking about two things. So we're going to make this our definition of a triple integral. So as delta v sub I approaches 0, we get the triple integral over Q, our volume, of dx, dy, dz. And we could call this little element dv. So that would be our volume of our solid. If we have some function that we're putting in there, that we're multiplying this delta x sub I, delta y sub I, delta z sub I, we could say our triple integral so if f of x sub I, y sub I, z sub I, if we had some function, a density function, something like that, our triple integral would be the triple integral over our region of f of x, y, z dv. And in this particular instance, our dx, dy, dz would be dv. So this would be the triple integral of f over our region Q. So we're defining it in the same way that we defined a double integral. And we're going to evaluate triple integrals with a theorem similar to Fubini's theorem. We're going to evaluate them as iterated integrals. So we just have 3 iterated integrals rather than 2 iterated integrals. So questions on our development here. All right. So our triple integral is the limit of this sum as delta v approaches 0, just like with our double integral. We're going to evaluate them the same way we did with double integrals. Triple integrals have similar properties to single integrals. There's nothing really surprising about the way they work. If you want to look at some of their properties, some of the more important ones are listed on page 1009. But the properties of triple integrals are very, very much like the properties of single integrals. So if our solid region can be divided into rectangular prisms easily, then, like I said, we evaluate our triple integrals like we did our double integrals. We evaluate them as an iterated integral. So if we have a nice region, we can divide them into rectangular prisms. dv, and I'm going to say for nice rectangular regions, dv, our little volume element, is going to be some permutation of dx, dy, dz. So for triple integrals, we have 6 possibilities for our order of integration. We can integrate in any of the 6 orders that we could rearrange these things. Usually, if you're dealing with regions that you're dividing into rectangular prisms, usually we're going to use the order dx, dy, dz. So I want to go the other way. dz, dx, dy, or dz, dy, dx. And that makes the reason we do it this way is this dx, dy, or this dy, dx is exactly like our region in the xy plane that we've been dealing with for double integrals. So this is R in the xy plane. So what happens when we evaluate our integrals in this order is we evaluate that first integral with respect to z, and then we just have our familiar double integral that we evaluate over a region R in the xy plane. So that's why we usually evaluate them in this order. So for example, if A is less than or equal to X, less than or equal to B, I'm just going to write how we're going to set one of these up. And we have H1 of X less than or equal to Y, which is less than or equal to H2 of X. So Y varies between H1 and H2. And G1 of XY less than or equal to Z less than or equal to G2 of XY. So Z is varying from G1 to G2. Then our triple integral becomes triple integral over our region of f of x, y, z dv is the integral from a to b, the integral from h1 of x to h2 of x, the integral from g1 of xy to g2 of xy, f of x, y, z, dz, dy, dx. And we evaluate each iterated integral by holding the other two variables constant. So our setup is exactly like we've done with double integrals. We just add this third integral inside. And what triple integrals are going to allow us to do is, one, we can set triple integrals up to find volume fairly easily. The volume is just going to be the triple integral of dz, dy, dx. We'll talk a little later about our f of x, y, z being a density function, or so we can find the mass of a solid region with a variable density by setting up a triple integral, and we can find moments of a solid about various axes and about various planes by evaluating a triple integral. And when we start talking about different coordinate systems, cylindrical coordinates or spherical coordinates, setting up our integral and our limits of integration, if we have nice symmetry, a spherical symmetry or a cylindrical symmetry, our triple integrals are extremely easy to set up because the limits of integration really tell it, the shape tells us our limits of integration right away. We don't have to worry about projections into the planes and all of that kind of thing. All right, questions on our setup here? All right, let's look at a couple of examples, and then I want to talk about some applications. So first, let's just evaluate a triple integral. So we want to evaluate this thing. So we do it inside out, just like we did our double integrals. So we're going to evaluate the integral of x with respect to z. So integral of x dz. So what do we get there? We just get xz. xz, and z is varying from 0 to xy. So that's our first evaluation. And it can be very helpful to write your variables when you do your limits here, to remind yourself which one we're substituting in here for. So z is varying from 0 to xy, so this becomes the integral from 0 to 1, the integral from 0 to x. When I evaluate xz from 0 to xy, I get x squared y. And now we have a double integral that should be more familiar with. So this evaluates to 0 to 1. I'm evaluating the integral of x squared y dy. So what do I get there? X squared, we're integrating with respect to y. So x is a constant. So I get x squared y squared over 2. I'm evaluating with respect to y. And we're evaluating y equals 0 to x. So when I let y vary from 0 to x here, when I plug in my limits of integration, y equals 0 to x, I get x to the 4th over 2. I'm plugging in x for y squared at my endpoints. And this is going to evaluate to x to the 5th over 10 from 0 to 1, and I get 1/10. So that triple integral would evaluate to 1/10. Questions on our process there? So one thing just to be careful with these triple integrals, because you have so many integrals going on, it can be very helpful to make sure you're paying attention to which variable you're integrating with respect to. Do some little notation to help you out. And when you evaluate your integrals at your limits of integration, to remember to substitute for the correct variable. So that's why I put the z equals 0 to xy, y equals 0 to x, to remind myself which variable I need to substitute in for. All right, let's look at another one. So let's find the volume and we're just going to set this one up. We're not going to evaluate this. Find the volume of the solid bounded by z equals 9 minus x squared, z equals 0, y equals 0, and y equals 2x. So we need to figure out what this solid, what we're talking about here, so we can set up our integration. So first off, z equals 9 minus x squared. What kind of solid is that? Upside down parabola. And since we're missing the y coordinate, what does that tell us? This would be a cylinder. It's a cylindrical surface about the y-axis. So z equals 9 minus x squared. I get a parabola like so, and it would go back into the other half would be back here. I'm just going to draw the front half here. And it goes along the y-axis. So we have this parabolic cylinder like so. And then y equals 2x is going to be this line in the xy plane. Z equals 9 minus x squared. And what's this point going to be on the x-axis? When z equals 0, x equals z equals 0, 3. So we get x equals 3 there. And so our region in the xy plane is going to be this little piece here. That's our region in the XY plane. So let me draw a sketch of that region. So there's our region. So what we're thinking here is we're going to let z vary from 0 up to the surface. Y is going to vary from 0 to the line here. And x is going to vary from 0 to 3. So we're making our little, in the xy plane, we're making our little rectangles vertical. We're integrating with respect to y up the rectangle. We're integrating with respect to x across the region, and then we're integrating with respect to z up to the surface. So our integral, our volume, is going to be the triple integral from x equals 0 to 3, y equals 0 to 2x, z equals 0 to 9 minus x squared, dz, dy, dx. And once we evaluate this first integral with respect to z, then we would have how we would set this problem up using a double integral. The volume of the solid bounded by f of xy, and this would be our region in the xy plane. So once we evaluate that first integral, we get to the double integrals that we've been working with for a couple of sections now. So we're letting z go from 0 to our surface. We're letting y go from 0 to 2x. And then we're letting x go from 0 to 3 across our region. So that would be our volume. Questions there? So with triple integrals, it becomes even more important to be able to be familiar with your surfaces, to be able to sketch your surfaces so you can figure out your limits of integration if the problem is given to you in this kind of format. All right, let's go the other way. Let's go from a triple integral to a sketch of the region. So we have the integral from 0 to 4, integral from 0 to 4 minus x over 2, and the integral from 0 to 12 minus 3x minus 6y over 4. And we have dz, dy, dx. And we want to sketch the region. All right, so the limits, from the limits of integration, limits of integration tell us x is between what and what here? X is between 0 and 4. That's the outer integral. 0 less than or equal to x, less than or equal to 4. And y varies, y is between what and what? 0 and 4 minus x over 2. That's our second integral. 0 is less than or equal to y, less than or equal to 4 minus x over 2. And finally, our inner integral tells us that 0 is less than or equal to z, less than or equal to 12 minus 3x minus 6y over 4. So what kind of surface is z equals 12 minus 3x minus 6y over 4? It's going to be a plane. We're linear in x, y, and z. I can rearrange this and say z equals at our upper limit of integration, z equals, I'm going to just write this as our standard equation of a plane, 3x plus 6y plus 4z equals 12. So that would be our equation of our plane from the upper limit of integration. So now we can sketch our region. So here are our axes. So how do we sketch a plane? What's our technique for sketching a plane? I'm going to let y and z be 0. When y and z are 0, x equals 4. So I get a point here on the x-axis at x equals 4. When x and z are 0, y equals 2. So I get a point over here at y equals 2. And when x and y are 0, z equals 3. So I get a point up here at 3. So we have the plane. Our plane looks like this. So there's the region that we're talking about. X goes from 0 to 4. Y goes from 0 to this line in the xy plane would be y equals 4 minus x over 2. And then the plane is our surface. 3x plus 6y minus 4z equals 12. That would be our surface. So that's our region. Now let's see if we can do this part. Let's rewrite in the order, we want to change our order of integration, dy, dx, dz. So we want to rewrite our order of integration. So the way we can think about this one is when we have our order of integration dz, dy, dx, this dy dx is our region in the xy plane. So that's this little triangle in the xy plane. That would be this. Well, in this order of integration, this is a region in the xz plane. So we're talking about this little triangle over here. And y, we're thinking of y as our height above the plane. So y is our distance to our surface. So our region that we're talking about here is this little triangle in the xz plane, and y is our height function. You can think of it that way. So we need to get our plane expressed in terms of y equals. So that will tell us how far this plane is from the surface. That's the y distance. We can rewrite the plane, the equation of the plane, into y equals form, and then we can find this region in the xz plane from the equation of the plane as well. When in the xz plane, y equals 0, and we can get an equation for this line to give us our boundaries in the xz plane. So from our equation of the plane, from 3x plus 6y plus 6z what do we have? 3x plus 6y plus 4z equals 12. We can solve this and we get y is going to be less than or equal to 12 minus 3x minus 4z over 6. So that tells us this distance from this plane, this little triangle, up to our surface. And in the xz plane, we can let y equal 0 here, and we get the equation of this line. So we get x is less than or equal to 12 minus 4z over 3. So the equation of this line would be x equals 12 minus 4z over 3. So now we can rewrite our order of integration. We can say our volume, and I'm going to put my three integrals here where our order is going to be dy, dx, dz. So y is going to vary from 0 to 12 minus 3x minus 4z over 6. X is going to vary from 0 to 12 minus 4z over 3. And z is going to vary from 0 to 3. Z is varying from 0 to 3 in that little triangle. So that would be our order written dy, dx, dz. So changing order of integration in triple integrals, a little more challenging. A little more challenging. Have to think about the geometry of the situation a little more. Fortunately, for the most part, we can always set up our triple integrals in the order dz, dy, dx. And then we can think of that dy, dx as our region in the xy plane. The way we like to think about that. All right, questions there? All right, let's talk about a few applications of triple integrals. Triple integrals make finding mass and moments of inertia of solid regions very easy. So now when we talked about centers of mass and moments before, when we talked about planar lamina, we said rho, our density function, was mass per unit area. Now we're going to say that rho is a function of x, y, and z. And we're talking about mass per unit volume. So our mass, using a triple integral, the mass of a solid region is going to be the triple integral over our region of rho dV. Our moment about the YZ plane is a triple integral over our region. The distance from the YZ plane is x. So this is our moment. Let me put a label here. This is our first moment. So this is our moment about the YZ plane. So we defined a moment as the mass times its distance from an axis. Well, here our axis is the YZ plane. We're weighting this by the distance from its distance from the YZ plane. The moment about the XZ plane, the distance from the XZ plane is y. So we have our same triple integral over our region, y, times our density function, dV. So this is about the xy plane. xz, this should be xz, sorry. So that's our moment about the xz plane and the moment about the xy plane. Distance from the xy plane is z. Triple integral q, z times our density function. So that's about the xy plane. And then our center of mass is x bar is m sub yz over m. Y bar is m sub xz over m. And z bar is m sub xy over m. So that would be the coordinates of my center of mass of this solid region. And we evaluate these just like we've evaluated iterated integrals in the past. Plug in our functions and evaluate our iterated integrals. We're going to do this a similar thing for our second moments, our moments of inertia. So this our first moment. We're weighting by its distance from the various planes. The second moments we weight by the square of the distance. So that gives us our moment of inertia of this solid region. So our second moments, or moments of inertia, I sub x about the x-axis is going to be our triple integral over our region. Distance from the x-axis is y squared plus z squared. So this is about x-axis. And the same thing for the y and z-axis. Same triple integral. Distance from the y-axis is x squared plus z squared. And I sub z, same setup. So that would be our moment of inertia about the z-axis. We can also define our second moments about the various planes. So we can talk about the distance of the mass from the various planes. So we can define our second moments as second moments about our coordinate planes. So we'll write those out. I sub xy is the triple integral over our region. The distance from the xy plane is z, and we're weighting it by the square of the distance. I sub xz is the distance. The distance from the xz plane is y. So that would be y squared rho of xyz dv. And finally, which combination do we have? xy, xz, yz is going to be our triple integral. The distance from the yz plane is x. And from these definitions, we can see if we look at if we look at these integrals and we look at these integrals, we see that these integrals are the sum of two of these others. It's usually easier to calculate I sub x equals I sub xy plus I sub xz. It's usually easier to find our moment about the axis by doing the sum of these two integrals. I sub y is going to be I sub yz plus I sub xy, and I sub z is going to be I sub xz plus I sub yz. These are usually going to be easier to calculate. Because evaluating these integrals with the sums can be more difficult than evaluating each of these individually and then using those to find your moments about the axis. All right, questions on the second moments? Same definition, same setup. We're just evaluating a triple integral rather than a double integral. All right, I want to talk about I want to set up one example. We won't have time to go through it. That is in the additional examples, but I want to talk about the setup for this next problem. We want to find the center of mass. And what we're given is this picture. So we want to find the center of mass of this solid region bounded by, in the first octant, bounded by this surface. So that's our setup. That's all we're given. What do we need to do here? What are we missing? Well, we can figure out our region in the xy plane. We could figure out an equation for that line, right? That would be easy. So that could give us our y varies from 0 to that line. We know that x varies from 0 to 5. But what about z? Z is going to vary from 0 to this surface, but we don't have an expression for that surface. It's a plane. The surface is a plane. How can we find an equation for that plane? What do we need to write an equation for a plane? We need what? We need a point. Well, we got 3 to choose from here. So we have 3 points on the plane. What else do we need to write the equation of a plane? We need a vector. Oh, thank goodness we have vectors coming back. We need a vector. What kind of vector? A normal vector. We need a normal vector for our plane. How are we going to find a normal vector to this plane? We have 3 vectors here to choose from that are on the plane. I can turn this segment into a vector. I'm going to call that vector P. going to call that vector Q. And then we can form the cross product of these two vectors and get a normal vector to the plane. P cross Q will be normal to the plane. So we have our point, we have a normal vector, we can use the point and the normal vector to write the equation of our plane, and then we can figure out our limits for our triple integral, our limits for z for our triple integral to find our center of mass. And here we're assuming that rho is just a constant. So rho is not a variable. So this would be how we would set this problem up. I worked through the rest of this problem in this video, Calc 3 2013 14.6 additional examples. So I worked through the rest of that to find the calculations, to find the center of mass of this region. All right, I could hear everyone breathing a sigh of relief that we finally got to use vectors in chapter 14. All right, homework. We also get to renew our love of homework over spring break.
I just remember it's going to be a lot of homework.
It's not a lot of homework. There we go.